Hi everyone, my name is Logan Clark and I'm a PhD candidate at the University of Virginia working with Dr. Sara Riggs. I'm really excited to share some of the work we've done studying reaching behaviors in VR. Now, reaching is one of the most common types of movement behavior. Most of us perform hundreds of reaching movements every day, whether that's reaching for a handle to open a door or reaching for our favorite mug to take a sip of coffee. Now, reaching movements are also a really common way of interacting with virtual objects in VR. With virtual hand reaching techniques, many modern VR systems map the position of our hands or handheld controllers to a set of virtual hands that we can use to interact with virtual objects the same way that we'd reach to and interact with their physical version. Now, motor control researchers over the past several decades have found that if we track the position of a person's hand while they're reaching, we can analyze the position data in several different ways to look at different properties of a person's reaching movements. We call these kinematic properties since they measure different aspects of how a person's hand moves during a reaching movement. Kinematic properties of reaching movements can tell us things like how efficient, fast, or smooth a person's reach is, and they can also reveal the types of strategies that people use to plan and complete their reaching movements. Now in this work, we focused on studying the kinematic properties of reaching movements performed in VR. And thankfully, this is pretty easy to do since many VR systems already track the position of a person's hands, or at the very least, the position of handheld controllers, while people are performing virtual hand interactions. Specifically, we wanted to understand how the kinematic properties of reaching movements may change when people reach in different directions. So for example, how might the kinematic properties of a reach be different if this person starts with their hand here and reaches upward, compared to if they started with their hand at that same spot and reached downward? Now, as we discuss at length in the paper, there's quite a bit of reason to think that the answer to this question may be that it depends. First, it could depend on which side of the body the movement's occurring on. So reaching upward on one side of the body might be different from reaching upward on the other side of the body. Second, it could also depend on which hand our person is using to perform the movement. So reaching upward with their dominant hand could be different than reaching upward with their non-dominant hand. So given all of this, we examined how these three factors interact to influence the kinematic properties of reaching movements performed in VR. This figure here shows a conceptual model of how we suspect these factors might interact. As we discussed in the paper, there's reason to think that several kinematic properties of reaching movements may change when people reach in different directions, but these effects may be different depending on which hand the person is using and which side of the body the movement's occurring on. So what about this was new? Well, specifically, this research provided the first look at how the kinematic properties of reaches change when people reach in different directions on both sides of their body and using both hands. Researchers in the past have examined how the kinematic properties of reaches in the physical world or in VR may change when we vary one or even two of these factors, but it's not yet clear if or how all three of these factors might interact to influence people's reaching behaviors. And there are several reasons that we should care about that. So first, there are several practical uses for analyzing the kinematic properties of reaches performed in VR. This includes uses in VR-based telehealth programs, in VR-based motor skills training, and for possibly even for detecting usability issues in VR interfaces. Now, in all these contexts, understanding how the kinematic properties of people's reaches change across different conditions can help practitioners to use these types of analyses more appropriately. And then second, as VR systems become more widespread, there's been a lot of interest in figuring out how to extend models of reaching performance, like Fitts' law, to predict how people will perform when they reach to objects in VR. These models, as I'm sure many of you are aware, are important tools for developing and testing new types of interfaces. However, the models that have worked in the past for simpler 2D interactions don't always seem to work as well for 3D reaches in VR. However, understanding how the properties of reaches change when people reach in different conditions in VR could help to give us some clues about how to model and predict these types of behaviors better. So, the current work, we examined how several kinematic properties of reaches change when people reached in 5 different directions on both sides of their body using both hands. In this study, we had participants perform a simple reaching task in VR using an Oculus Quest 2 headset and a handheld controller. The movement of the controller was mapped to the position of a virtual hand, so participants could reach to objects in VR just as if they were using their physical hand. In this task, participants began each reach by moving the fingertip of their virtual hand to a yellow start sphere. When they were ready to start the reach, they pressed a button on their handheld controller to select the start sphere, and the start sphere would disappear and a red target would appear at one of several possible locations. They'd then reach to the target and press a button on their controller to select it. Once a target was selected, it would disappear and the start sphere would come back so participants could begin the next reach. Now if we unpause, here's what the task looked like in closer to real time, selecting start, then target, then start, then target. Now for this study, we had 20 young right-handed participants reach in 5 different directions, up, down, left, right, and away, and they performed these reaches on both sides of their body using both hands. This gave us a 5x2x2 repeated measures design. Now at the beginning of the study, participants completed a practice session to get familiar with the task, and then they completed 4 sessions of our VR reaching task. Each of the 4 sessions involved one of the possible combinations of hand and side, and the order of these 4 sessions was counterbalanced across participants using a Latin square design. During each session, participants performed 10 reaches in each direction, and the directions appeared in a random order. So we then calculated 6 different kinematic properties for each reach, and we used multi-level linear models to see if and how each of these properties changed when people reached in the different conditions. For this presentation, we'll just focus on one of these properties, which is called movement time, which will basically just give us a simple example we can hold on to as we talk about the result. I'm sure many of you are already familiar with the concept of movement time, but in short, movement time is simply the amount of time somebody is moving while they're performing a reach. It cuts out the reaction time at the beginning of the task when the target has appeared but the person hasn't started moving, and the confirmation time at the end of the task when their hand has already reached the target, but they have not yet pushed the button to select it. So what do we find? Well, looking at our results for movement time, we saw a significant main effect of movement direction on movement time. This told us that movement time changed significantly across reaches in the 5 different directions. However, we also saw a significant direction by hand by side interaction. This indicated that movement time changed differently across reaches in the 5 different directions, depending on both which hand people used to perform reaches and which side of the body these reaches occurred on. This was representative of a pattern that we saw for several of the other kinematic properties as well, and I'd encourage you to check out our paper for a detailed summary of those results. Now importantly, these results revealed for the first time that several kinematic properties of reaching movements can change depending on the direction a person reaches, the hand they use, and the side of the body where the movement occurs. We were also able to take a look at how the kinematic properties of people's reaches change across these different conditions. And we provided a complete breakdown of these results for each kinematic property in our paper. So for example, looking at our results for movement time, we were able to see how movement time changes when people reach in the 5 different directions, and how this was different for reaches on each side of the body using each hand. So what were the implications of this work? Well, most immediately, as practitioners continue to move ahead with analyzing the kinematic properties of reaches to measure things like arm function in stroke patients, our results here show that some of the kinematic properties they may want to use can be sensitive to more than just what they're intended to measure. Specifically, many of the most commonly used kinematic properties can change depending on the direction a person's reaching, the hand they're using, and the side of the body where the reaches occur. Practitioners might need to take this into account when they're interpreting kinematic results, but it might also be worthwhile to develop some new kinematic metrics that can measure things like arm function without being sensitive to changes in factors like movement direction, hand, and side. And then second, as we continue to work on finding ways to accurately predict movement performance for reaching interactions in VR, we might need to look to models that can account for how factors like movement direction influence people's reaching performance. More complex models, like those based on optimal feedback control theory, might be especially useful for this. So that's all I have to share today. Thank you to Peiyu Zhang and Jeffrey Rickbart for developing the software we use for this work, and to Meta for the fellowship funding.